Okay, so this second example is designed to show you how to deal with unbalanced data. So I have some data on bankruptcy at Polish companies, and the data is in a weird file called ARFF. Luckily, there's a library called Foreign that lets you read in all sorts of weird and wonderful formats. And one of the functions in Foreign is read.arff. So let's just run that. Let's just kind of have a view of this data. So basically includes all different types of financial ratios for a company. Let's move along. And it contains a class which is 1 if the company was bankrupt and 0 if it wasn't bankrupt. Now, these aren't randomly ordered, um, but you can see that there's mostly non-bankrupt and a few that are actually bankrupt. And I have the actual the description of the columns down here for the accounting students in the class. So we have all this information on bankruptcy, and then when we have whether or not a company is bankrupt or not. Now, let's just have a look at the levels of the class. 0 is non-bankrupt and 1 is bankrupt. Let's just set them. Remember I said Care likes class descriptions rather than 0 and 1s. So we set the levels of the classes. We can actually just see how much we have of each with the table command. And you see that 271 are bankrupt, 6756 are bankrupt. Now, this file here is actually, there were 5 files in the original data set. This is the hardest to predict because it's basically, we have 5 years of data, and then after year 5, we see if a company is bankrupt or not. So we're taking basically ratios from 5 years ago and then seeing if a company was bankrupt in 5 years' time. So let's kind of go a little bit further. Now, there is some missing data. So let's just find the number of rows and columns. And what proportion of data is missing? About 1%. But if we did like complete cases, because again, the missing data is distributed, we'd lose over half the data. We're not going to bother with the mean imputation like the last file. We're just going to go straight to mice. This was a real pain to actually get mice working and returning all the data. It couldn't work out a few of the missing values. But I found these parameters that would do it for me, but I'm looking on some forums. Let's just run mice. And we're just, again, in practice, you would want to get m equals a larger number. You might want m equals 10 imputations. And then combine the data for your training models. We're going to keep it simple in this class. We're just going to have one estimate of the missing data, which is what we call a single imputation. I'll just pause the video while we. Okay, let's just see if any of the missing data, the data is missing. We have to use complete, and then we basically sum all of these values. And you can see there's no missing data left. If we still had 1 or 2 missing entries, mouse had like fallen to pieces on. What we could have done is then having filled in most of the missing data, we could have just made sure there was no missing data using complete.cases. So, and this won't actually do anything here because we have no missing data. So if you look at my data too, let's just look how much data we have. Dim is the same as doing n rows and n columns. We still have exactly the same rows and columns as before. We've not lost anything. Okay, as we're doing k-nearest neighbors, we're not messing around this time with scaled and non-scaled versions. We're just going to scale all the numeric version. Ncols is just the last column with the class, so we're basically scaling everything except the class. We did the train control, and we're going to do k-nearest neighbors. Note this time I've got the 2-class summary because this is basically a very unbalanced data set. I want to compare the specificity and the sensitivity. And recall we have the metric equals ROC. Then we're just going to run this. Again, I'll just pause the video. Okay, so let's just see what we've got. And some of it may be a little bit surprising. The first thing is that the sensitivity, how well we're predicting the ones, is really high. And the specificity is really low. Now, what's happened is it's basically got the classes the wrong way round. This two-class summary, what it does is it automatically assigns the classes. And it's in this case, it's got them the wrong way round. Now, what we can do is we can manually do the confusion matrix. So we can put the knfit pred and the knfit pred obs. So let's just take this. Let's just see what we got. We could view it. And you see Caret for the K nearest neighborhood, it doesn't actually return the probabilities, but it returns the predictions and the observations and the actual what it takes as the false and the trues, and then the row it was taken from. Okay, so we could actually then just kind of match the predictions and the observations, as we've done many times before, put them in a confusion matrix, tell them explicitly we want the positive to be true, i.e. bankrupt, and there we get the proper values. So we can get the specificity, how well we find the not bankrupt companies as as 99%, and the sensitivity of 0.02. And this is because K nearest neighbors, if the kind of the sets are not really well defined, most neighborhoods are going to have mostly not bankrupt companies. So we're going to predict not bankrupt companies nearly all the time. So we're really good at predicting non-bankruptcy, but most bankrupt companies, we actually say, oh, they're bankrupt. So there's a way around this, and one of these is to do something called oversampling. And what we do is we look at the bankrupt companies when we're building our training data sets, and we literally oversample them. We kind of repeatedly sample the bankrupt companies. So we end up with about 50% non-bankrupt and 50% bankrupt using the model. And one way of doing this, we can run this manually, but for simplicity for this project, if you have a really unbalanced class, all you need to do is put sampling equals smote. Smote is a type of oversampling technique. And this will create training sets with 50% bankrupt and 50% non-bankrupt. Now let's just see if we do any better with this. Okay, just pause the video. Okay, now let's look at the fit from this version where we have the oversampling. And we can see a huge difference. The sensitivity is maybe not quite as high, but as we increase the value of K, then our specificity increases. So let's just try and see what happens. It picks a value of K equals 10 here. Note to get this output, we need to put summary function equals two-class function. And on the train, we need to do the metric equals ROC, which is the area above the random sensitivity specificity line. So let's just run this, our confusion matrix. And you can see, this new model, we've done much better in sensitivity. The whole point of this exercise is to find bankrupt companies. And our previous model had good accuracy, but it couldn't find bankrupt companies. So this might not be maybe quite as accurate, but it does a much better job at sensitivity, at finding bankrupt companies. The final little part of this example is, I ask you in the project document to utilize additional techniques. Now, one easy way of doing this is if you go to the Caret documentation, I've given you a link here, but if you go to the Caret documentation, the train models, it gives you a list of all the different models that can be implemented in Caret. So this is a lot of models. So for, you can pick one of these. If you've got like a class classification, such as the going concern prediction, you want classification. If you're predicting a number like your NFL yards per carry, then you want regression. And you can just pick one of these techniques and see how well it performs. And you could maybe do a little search in Google to look at the documentation and have a few line summary of what it does. So I actually I've just built a neural network model. And what a neural network model does is I found a little thing here. It's basically our brains consist of neurons. And anything we view, any kind of stimuli, is translated back to actions through neurons after being converted into electrical signals. So say, for example, I see some food, it looks good. That will be transferred back to my brain, and my brain would have a desire to eat the food, and I would go ahead and eat the food. And these neural networks are slowly trained over time. So as a little kid, as a toddler, as we begin to experience the world, our neural networks are slowly kind of training themselves as we kind of develop new stimuli and develop new skills. So this is really just an artificial brain. What happens is we have our data. So it's actually the same format as before. We have our independent variables, in this case, all the financial information. Then we have some neurons in between this data and our dependent variable, which is the bankruptcy prediction. And the neural network training just slowly builds up these neurons so we can actually predict the bankruptcy or non-bankruptcy from the financial data. So just think of it as a very simplified artificial brain. And here, our one parameter is just the size of the neural network, how many layers the neural network has. So don't worry about it too much, but just see what we get. So we've just got 3 different sizes of neural network here. Just for interest, when you have, so we're actually implementing MLP. This will tell you the package that we're actually using. And one thing to work out the parameters is just do a search for this particular package. So just for example here, just search RNSR, and then you would get actually the documentation for RSNSS, the reference manual. And this will actually tell you, you could actually look here and you could look at the MLP function used by Caret, and this will tell you about all the different parameters you can use. So it gets quite complicated, but here there was just one important parameter, which was the number of kind of how big my artificial brain is. So I run this, and it takes a while, so I ran it before. And you can see here that the neural network does really well on the specificity, so it does much better on predicting bankruptcy. So it actually performs really, really well. And we can have the confusion matrix, and then we can look how well it performs overall. And you can see, look, if I'm predicting bankruptcies, sensitivities, this predicts over 50% of bankruptcies. So it's a lot better than the other techniques. But the specificity, it's still reasonably good, but it's maybe not quite as good as a few of the other techniques. So that's just how to introduce another technique in Caret. Just look at the Caret documentation, find something that looks interesting to you. You can it tells you the package. You need to make sure that you install this package before running it. So I've installed RSNSS here. And then it will actually tell you the parameter that's important. And you can go to the documentation for the package, and it will tell you a little bit more about the parameter. So literally, just kind of on the subject of how we've only covered a little bit in this class compared to what you can learn in machine learning, there's literally just hundreds of different prediction techniques available here. And I'm happy to kind of recommend 1 or 2 of these to your group. Okay, so we covered oversampling and unbalanced classes, and we covered how to get additional techniques in Caret.